Welcome to the deep dive. Chemistry. I mean, it's the study of matter interactions. It can feel like a huge subject.
Oh, absolutely.
And you're
Vast.
probably looking for a way to, grasp the core ideas without drowning in details.
Which is exactly what we're aiming for today.
Great.
We're diving into some fundamental chemistry concepts. We've pulled together a bunch of sources. Some are specific problems, others more like broad overviews.
And the mission.
The mission is really to pull out those key insights, the aha moments, things that help build a solid foundation. We're talking states of matter, bonding, reaction dynamics, energy, all that good stuff.
Okay, sounds like a plan. Let's start with something pretty basic. Gases. We've got this graph here looking at how an ideal gas's pressure changes with volume at different temperatures.
Right.
It shows the hotter the gas, the steeper that pressure volume curve is. What's the core idea there?
Well, it's a fantastic illustration of the ideal gas law, PV, NRT. It really is. Think about it. Higher temperature means the gas molecules have more kinetic energy. They're zipping around faster, hitting the container walls harder.
Right, more energy.
So for the same volume, a hotter gas just exerts more pressure, that steeper slope. It's showing you visually how pressure responds more strongly to volume changes when it's hotter.
That makes intuitive sense. More energy, harder hits. Now, another question looks at an ideal gas expanding isothermally,
Isothermally, yeah.
which just means constant temperature, right?
Exactly. Temperature doesn't change.
So if this gas expands and it's absorbing heat while doing it, where's that heat energy actually going?
That's a key point for ideal gases. Since it's isothermal, the internal energy isn't changing because for an ideal gas, internal energy only depends on temperature.
Okay.
So if heat is coming in, but the internal energy stays the same, that energy has to be going somewhere. It's being used entirely to do work on the surroundings as the gas pushes outwards as it expands.
Wow, okay. So heat in, work out, and the gas itself stays at the same energy level.
Precisely.
Yeah.
It's like a direct conversion of heat to mechanical work at the molecular level.
Interesting. Okay, what about gas mixtures? We have the scenario with hydrogen and oxygen mixed together, and we know the total pressure.
hmm
How do we figure out, like, the pressure just from the hydrogen or just from the oxygen? Sounds like Dalton's law.
That's exactly it. Dalton's law of partial pressures. It's pretty straightforward, actually.
Yeah.
Just says the total pressure is the sum of the pressures each gas would exert if it were all alone in that same container.
Right.
So to find the individual or partial pressure of each gas, you need its mole fraction.
Mole fraction. So, like, what percentage of the molecules are hydrogen, what percentage are oxygen?
Exactly that. The proportion of the total moles. The question gives weight percentages, so first step is converting grams to moles using their molar masses.
Got it.
Then calculate the mole fraction for each, multiply that fraction by the total pressure, and boom, you have the partial pressure for that gas.
So the lighter gas, hydrogen, even if it weighs less overall, might contribute more pressure if there are more moles of it.
Precisely. It's about the number of molecules bouncing around, not just their individual weight. More molecules, more collisions, more pressure contribution.
Okay, that clicks. Now, ideal gases are, well, ideal. They're a model. Real gases aren't always perfect.
Very true. They deviate.
There's a table showing PVRT isn't always equal to 1 for a mole of gas. What's that telling us?
That value, PVRT, that's what we call the compressibility factor, Z.
Z. Oh,
For a truly ideal gas, Z is always 1, no matter what. So when we see Z deviating from 1, it's a clear signal the gas isn't behaving ideally.
and why wouldn't it?
Well, the ideal gas law makes two big assumptions that aren't quite true in reality. First, it assumes gas molecules have zero volume themselves.
Which they don't, obviously.
Right. And second, it assumes there are absolutely no attractive or repulsive forces between the molecules.
Also not quite true.
Exactly. So at really high pressures, the molecules get squeezed together and their actual volume starts to matter relative to the container volume. And at lower temperatures, molecules move slower, so those intermolecular attractions have more time to take effect. So those factors cause the Z value to shift away from 1. They do. And different gases deviate differently depending on their molecular size and the strength of their intermolecular forces. Some other questions look into this, showing how, say, helium might behave differently than ammonia under the same non-ideal conditions. Helium, for instance, often shows Z greater than 1 at high pressure because repulsion dominates when they're squeezed tight.
Okay, real-world complications. Let's shift to how these molecules move around. Diffusion. There's a mention of carbon dioxide, CO2, and phosphorus trichloride. PCl3 and their molecular weights. How does weight connect to how fast they spread out?
That's Graham's law of diffusion, or effusion, technically, escaping through a small hole, but the principle's the same for spreading out.
Okay, Graham's law.
It states that, at the same temperature and pressure, lighter gas molecules move and diffuse faster than heavier ones.
Why is that?
It comes down to kinetic energy. At the same temperature, all gases have the same average kinetic energy.
Right.
And kinetic energy is half times mass times velocity squared, 12 milliVar. So if the average kinetic energy is the same, but the mass m is smaller, the average velocity v must be higher to compensate.
Lighter things have to move faster to have the same energy.
Exactly. CO2 is much lighter than PCl3, so its molecules, on average, are moving faster. They'll spread out more quickly. It's a useful principle, sometimes used to separate gases.
Fascinating. Okay, lighter means faster on the molecular level, too.
Let's switch gears completely. Chemical bonding, how atoms stick together.
Crucial stuff.
We have questions about dipole moments, molecules like ammonia, NH3, versus carbon disulfide, CS2. What do these dipole moments tell us about whether a molecule is, polar overall? Right, dipole moments are key to understanding molecular polarity. What's really insightful, I think, is that you can have polar bonds within a molecule.
Meaning, like, unequal sharing of electrons between two atoms.
Exactly. Unequal sharing creates a little separation of charge, a bond dipole. But the molecules as a whole might still be nonpolar.
How does that work?
It all comes down to the molecule's three-dimensional shape, its geometry.
The architecture.
Precisely. If the molecule is perfectly symmetrical, those individual bond dipoles can essentially pull in opposite directions and cancel each other out, like a tug-of-war where both sides are equally strong.
Okay.
So carbon disulfide, CS2, is linear. The CS bonds are polar, but they point in exactly opposite directions. Net result, zero dipole moment, nonpolar molecule.
And ammonia, NH3.
Ammonia has polar NH bonds, but it has that trigonal pyramidal shape, kind of like a little pyramid. It's not symmetrical.
Right, there's the lone pair on top.
Exactly. So the bond dipoles don't cancel. There's a net dipole moment pointing upwards towards the nitrogen and its lone pair. So ammonia is polar. Those examples with chlorinated ethanes really drive home how arranging polar bonds in 3D space changes everything.
So geometry is destiny for polarity, anyway.
Yeah.
Okay, another question mentions a molecule XY, gives its dipole moment and bond length, and talks about percent ionic character. How do we link those measurements to what the bond is actually like? Is it more shared electrons or more like one atom took the electrons?
Yeah, percent ionic character is trying to quantify that. Where does the bond fall on the spectrum between perfectly covalent equal sharing and perfectly ionic complete electron transfer?
Okay.
The measured dipole moment tells us how much charge separation there actually is. We can then calculate a theoretical dipole moment, assuming it was 100% ionic, like a full positive charge and a full negative charge separated by the bond length.
Right, the maximum possible separation.
Exactly. The percent ionic character is just the ratio of the actual measured dipole moment to that theoretical maximum ionic dipole moment times 100.
So it's like, how close is it to being fully ionic?
Pretty much. It tells you the degree of electron shift towards the more electronegative atom.
Got it. Now, bonding involves orbitals overlapping. We hear about sigma and pi bonds. What's the fundamental difference in how they form?
The difference is all about how the atomic orbitals overlap in space.
Okay.
A sigma bond forms from a direct, head-on overlap of orbitals right along the line connecting the two atoms' nuclei.
Head on, like a handshake.
That's a great analogy. It creates a strong concentration of electron density right between the atoms. Very stable.
And pi bonds.
Pi bonds form from the sideways overlap of p orbitals. Imagine two p orbitals standing parallel to each other, and they overlap above and below the axis connecting the nuclei.
Sideways overlap, so not as direct.
Not as direct, and the overlap isn't as effective. So pi bonds are generally weaker than sigma bonds. Sigma bonds are what you find in all single bonds. Pi bonds are the extra bonds in double and triple bonds. A double bond is 1 sigma plus 1 pi.
And a triple.
1 sigma plus 2 pi bonds. That weaker, more exposed nature of pi bonds often makes them sites of chemical reactivity.
Interesting. Head on for strength, sideways from making multiple bonds. Okay, what about hybridization? sp, sp2, sp3. It sounds complicated. Why do atoms even bother mixing their orbitals like that?
It sounds complicated, but it's actually atoms being smart in a way. They hybridize to form better, stronger bonds and achieve more stable molecular geometries.
Better bonds? How?
By mixing their basic atomic orbitals, like LETP,